All right, so here in section 8.5, we're talking about properties of logarithms. Now, some of these we already know, some of these we're going to learn for the first time. In class, we're going to go more over how these are true and why we know these are true. But for right now, I just want to introduce you to these properties. All right, so for some of these we can figure out ourselves, like the first couple of them. We know that for problem number 1, I could rewrite this in exponential form, right? I could say that b to some power equals 1. And we know that this answer is going to be 0, right? Any number to the 0 power would equal 1. So we know the answer to the first one is 0, right? We can think of another example to go along with it. Let's try log base 3 of 1. And again, we know that 3 to what power is 0? Is 1? Well, 3 to the 0 power is 1, right? So this is going to have to be an answer of 0. All right, again, b is just some letter, so b is a number, so b could be 5, 10, 1,000. All right, we are going to say that for these problems, b is greater than 0, and we're going to say that b is not equal to 1. All right, those are going to be some constraints on the base that we have. All right, so whatever you choose for your base, it has to be bigger than 0, but it cannot be 1. So you could choose something like 1/2 or 10 or 500. Problem number 2, log base b of b. So this is saying b to some power equals b. Well, it's going to have to be to the first power, right? b to the first power equals b. So this is going to have to be an answer of 1. For example, let's say I had log base 2 of 2. Well, this is saying 2 to what power equals 2? And that's got to be 2 to the first power. All right, so we can confirm that that's true. Let's try problem number 3. Problem number 3, well, this is saying that my base b to some power equals b to the a power. Well, what we know from the previous sections in chapter 8 about exponential equations is that we know that if I have the same base, I must also have the same exponent. So we know right away that the answer to this must be a. All right, whatever that exponent is, that's going to be your answer here. So we're going to write this as, we can do an example. Let's say log base 5 of 5 squared. And so again, we can think about this as 5 to what power equals 5 squared. We know that that answer is going to have to be 2. All right. Again, these examples are just confirming what we know to be true about these rules. All right, now number 4 is kind of an interesting one. Looks a little bit different. In problem number 4, my exponent is actually a logarithm. So this whole entire logarithm, log base b of a, is the exponent. All right, so a little bit different than what we're used to seeing, and we're going to explore this more in class as to why this is true, but the answer to this is a. All right, the rule is basically whenever your base here is the same as the base of this logarithm, then your answer, your exponent, is going to be the argument. So for example, if we use some numbers in there, we might be able to say 7 to the log base 7 of 1/2. Well, we know that because I have the same base here and here, my answer would have to also be 1/2. All right, so as long as these are matching up, that means that those will be matching up as well. And again, we'll explore that more in class. Number 5, now number 5, we had a special name for this. We already talked about this one. This one's called the change of base property. Change of base property. All right, we're going to use this in later sections when we're solving logarithmic and exponential equations. So we know that if I have a setup like this where a and b are both whole numbers, again, b is not equal to 1 and b is not equal, it has to be greater than 0. So I can say that this is the same as log of a over the log of b. All right, your base has to go on the bottom, and your argument a has to go in the numerator. All right, now the nice thing about this is you get to choose what you want your base to be. So I could leave it like this as a common logarithm. I could put in a base of 2 if I wanted. I could put in a base of 1/2 if I wanted. Right, you get to choose whatever that base is. So because you get to choose, I'm going to use the letter C. All right, so you get to choose what that letter is. So if we actually tried to simplify something like this, we could start with maybe, let's say log base 4 of 32. All right, now I can't solve this as it is because we're asking ourselves 4 to what power equals 32, and I don't know what that is off the top of my head. All right, so we're not going to be able to do that as it is, but using the change of base property, we can write this as the log of 32 over the log of 4. And now I'm looking here and I'm trying to figure out what would be a good base to choose, right? I want something that I could use exponents with to get 32 and to get 4. And so it would make the most sense to me to choose a base of 2. All right, this is helpful because now in the numerator I'm asking myself 2 to what power is 32, and in the denominator I'm asking myself 2 to what power equals 4. And I know that 2 to the 5th power is 32, 2 to the 2nd power is 4, so this would reduce to be 5 halves. All right, so using the change of base property is very useful to get rid of a logarithm and just change it to a number. All right, you sometimes will get a fraction, that's okay. All right, problem number 6. Again, we'll explore more why this is true in class. But for problem number 6, this rule is actually very useful when we're solving exponential and logarithmic equations. The rule for this is that if I have log base b of a to the n, now notice this is a little bit different than this one that we had here. Okay, so in question number 3, or problem number 3, notice the base of both of these is the same. In this problem, notice this base and this value a, those are different values. So the rule for this is going to be the same thing as n times log base b of a. What's happening is this exponent is coming out in front and being multiplied by that entire logarithm. All right, so this is a useful property when we're trying to simplify these logarithmic and exponential equations. And so kind of an example with some actual numbers. Let's say I have log base b. All right, sorry, let's pick some numbers. Let's do log base 2 of 8. All right, so log base 2 of 8, we know the answer should be 3, right? We know that 2 to what power is 8? Well, 2 to the 3rd power is 8, right? So we know this answer should be 3. But let's pretend we didn't know that for a second, and I just used this property. So what we said is that we could have, if I have a power here, so a to the n power, I can take this exponent and bring it out in front. And so if we look at this, I know that 8 is the same thing as 2 to the 3rd power. So this is really like log base 2 of 2 cubed. And so what this rule says is, again, I can take this exponent and bring it out in front of everything. And so this is really the same thing as 3 times log base 2 of 2. Now we know that log base 2 of 2 is just 1, right? That's the property we talked about right here. Whenever I have the same base and argument, that has to be 1. And so this is really the same thing as 3 times 1. And we know 3 times 1 is just 3. So we can verify this is a true statement because we expected to get 3, and of course we did actually get 3. Right? So anytime you have a number here, you could always try to change that number into a power of some sort. You might also be given problems where you're already given a power and you don't even have to worry about changing it. All right? But this is a great property to use. It helps you simplify these types of logarithmic expressions. All right, property number 7, this is one of the last two here. If I have log base b of m times n, the rule here is that this is the same thing as log base b of m plus log base b of n. All right, again, we'll talk more in class about why this rule is true, but this is the rule for now, just to give you some heads up. So basically, whenever you have two values that are multiplied together, or you have a product here, you can split that up into two separate logarithms with addition in between them. All right, notice a couple things. Notice that the base stays the same throughout. All right, you can't just change the base has to remain the same. And if we put some numbers to this, let's say we have log base b, numbers, base 2 of, let's do 32. All right, so again, we know the answer here should be 5, right? 2 to what power is 32? Well, 2 to the 5th power is 32. So we know the answer is 5 here, but let's try to use this product property to see if this is actually a true statement. So I'm going to split this up. We know that 32, I'm going to write it as the product of two numbers. So you could pick 4 times 8, you could pick 2 times 16, you could pick 1 times 32. Whatever two numbers you want to use. You could even do 64 times 1/2 if you wanted to. You get to pick whatever two numbers you want to multiply together. So let's say we did log base 2, and then let's do 4 times 8, how about? All right, well, if this is the value I choose for 4 times 8 is 32, I can break this apart into log base 2 of 4 plus log base 2 of 8, right? That's using this product property and splitting it up using addition. Notice how I keep the same base throughout. And if I evaluate these, we know that log base 2 of 4 is 2, because 2 squared is 4. We still got that plus. Log base 2 of 8 is 3, because 2 to the third is 8, and 2 plus 3, of course, is 5. All right, so if I add these together, 2 plus 3 is 5. Now again, like I said, you can use whatever values you want. We could take the same problem, log base 2 of 32, and we could split this up into two different ones, right? So this is really log of 2, and let's do 64 times 1/2, right? 64 times 1/2 is still 32, so this is working out for us. We're going to write this as log base 2 of 64 plus log base 2 of 1/2. Well, I know that 2 to the 6th power is 64, and I also know that 2 to the negative first power is 1/2, right? 2 to the negative first power is 1 over 2, right? I got to flip that base. So if I take 6 plus negative 1, well, 6 plus negative 1 is also 5, all right? So you can see it doesn't matter how you choose to break up that 32. As long as you use a product of two numbers, you're going to end up getting the same answer as long as you use this product property. All right, you might be able to guess that with division, we're going to use subtraction. So this is really the same thing as log base b of m. It has to be the numerator first, minus log base b of n. All right, if you had this would be incorrect. Log base b of n minus log base b of m, that would be incorrect. All right, the m has to come first, and then the n has to come second, all right? And then you're subtracting these two values. So let's try this again. Let's try something like log base, let's do a 3, how about? Let's do log base 3 of, how about 9? All right, log base 3 of 9. So we know the answer should be 2, right? We know that 3 squared is equal to 9, so the answer should be 2. So if we use this quotient property here, we can try to make sure that this is a true statement. So I'm going to write this as log base 3. And let's see, what are two numbers that divide to be 9? How about we do 27 divided by 3? Right, we know 27 divided by 3 is 9. So because I'm dividing here, I can write this as log base 3 of 27 minus log base 3 of 3. Notice my 27 came first, and my 3 came second. All right, I'm subtracting these because we're using division. So I can evaluate this. Log base 3 of 27 is 3. Log base 3 of 3 is 1. And 3 minus 1 is 2, just like we expected to get. Again, I could do this a different way. I could take log base 3 of 9, and I could split it up using two different numbers. We could, let's say, do log base 3 of 81 divided by 9, right? 81 divided by 9 equals 9. And if I split this up, this is going to be log base 3 of 81 minus log base 3 of 9. We know that this comes out to be 4 because 3 to the 4th power is 81. 3 squared is 9, which is kind of already answering our question. But either way, you can see that 4 minus 2 still equals 2. All right, so either way, no matter how you try to break up that value, as long as you're using division, you can subtract those two separate logarithms, keeping the same base, and you're going to get the same answer. All right, so these are all the properties we're going to briefly talk about now. When we get to class, when we get to the next set of homework, we're going to talk about how do we use these properties to solve exponential and logarithmic equations.